end of the last lecture on magnetic vector potential, we started our discussion on the multiple expansion of magnetic vector potential due to a closed current loop. So what we were considering is that current loop C prime, closed current loop C prime, which carries a steady current I. Our aim is to find out the vector potential at P having position vector R with respect to some suitably chosen origin O due to this current distribution. And the expression for the vector potential is this: A at R due to this current distribution is mu 0 I upon 4 pi integration contour integration over C prime dr prime upon R, which is mu 0 I upon 4 pi, and we expand this in binomial series and assuming that R is greater than R prime, and we introduce the Legendre polynomial L is equal to 0 to infinity R prime over R to the power L PL of cos theta. So cos of theta, where cos of theta is the angle this. Then we rewrite this as mu 0 I upon 4 pi R summation over L is equal to 0 to infinity 1 upon R to the power L integration R prime to the power L PL cos theta dr prime, or we write it as summation over L is equal to 0 to infinity AL of R, where AL is the nth multiple of vector potential and is defined as AL at R is equal to this R and this R together makes it mu 0 I upon 4 pi R to the power L, and the integration is we could perform the calculation without introducing Legendre polynomial, which has been outlined in the last class. Now it is interesting to note what is the value of AL for L is equal to 0. This becomes mu 0 I upon 4 pi R, and this part, this is integration over this is equal to 1 and this is equal to 1, so this is simply R prime and this is 0. This signifies that magnetic monopole does not exist. This. Now the second term, which is called the dipole term. Dipole term is L is equal to 1. This is equal to mu 0 I upon 4 pi R square, and the rest of the thing within integral is integration over C prime. This is R prime cos theta, as P1 of x is x. This is due to the fact P1 of x is equal to x, so P1 of cos theta is cos theta. You know that cos theta is the angle between R and R prime, so we could write it in a compact form like this. So we have what we have written, r dot r prime is r prime cos theta. So one r prime has been adjusted with this. So this is the dipole contribution to the vector potential for a closed current loop. Let me go a bit before going into the detail with the discussion of this. Let me consider a special case of Stokes theorem. Now we know that the Stokes theorem in its original form is this, integration a dot dr over a contour C is equal to curl a dot ds, where S is the surface bounded by the contour. We want to write this in terms of a scalar, so we write A as some scalar point functions times arbitrary constant vector, so that A dot dr is simply C dot phi dr, which is the form this. And so the right hand side is concerned, curl of A is equal to curl of phi times C. So this is phi times curl of C. Since C is a constant vector, this is 0 plus grad phi cross C. So we get curl A dot ds, which is the right hand side, is equal to, this is 0, so this is grad phi cross C dot ds. It is a scalar triple product, so that we can write it as C dot ds. So the Stokes theorem, using this and this Stokes theorem, now reduces to this is the form of Stokes theorem, and we like to use this theorem. But note that here we have used unprimed coordinates, but here the relation is in terms of prime coordinates, so there will be some difference, and let me write it there. This is the, and the integration is over ds prime, where ds prime is the surface bounded by the contour C. Cross, this is grad prime r dot r prime, and this part is simply r, because this is x prime plus y prime plus z prime. So whenever this nabla operates on it, it gives you simply r. So the result is mu 0 I upon 4 pi r cube the r is out of the integration sign. This is the form of vector potential, dipole contribution to the vector potential due to a closed current loop. If we have a current loop which lies in a plane, so if we have a current loop, extended current loop lying in a plane, then this integration gives you this area, and the direction of the area is governed by the right-handed corkscrew rule. Since it has been thrust in anti-clockwise direction. If we place a right-handed base of the right-handed corkscrew in the plane and rotate in the direction in which it is thrust, then in this case ds is directed towards the reader. But if we have a curve which does not lie on a plane, a contour which does not lie in a plane, in that case ds is the vector sum of the individual elementary areas. But one thing we can do, we can consider an elementary loop. The loop may not lie in a plane, the original loop may not lie in a plane, but we divide the entire loop. Say this is an entire loop which lies on a curved surface. We divide into a large number of pieces, and for each piece we consider each piece an elementary area ds, which can be approximated to lie on a plane. As we used to have a football ground on the earth's surface, similarly an elementary area even on a curved surface can be considered as a plane. So if we apply this concept to an elementary area, what happens? So dipole contribution, before going to that, if we consider the multipole expansion, we find that the monopole term is 0 and dipole term is the first non-vanishing term. So if it is in most of the cases it is sufficient to consider the dipole term only, and this approximation is called the dipole approximation. Such approximation we have already used in describing the polarization of dielectrics, and similar concept we shall use in future for describing the magnetization of magnetic materials. Now we come to dipole vector potential, dipole vector potential due to an elementary loop. We write it as this: delta A1. A1 signifies it is the dipole contribution, and delta signifies that the elementary loop. So we write it mu 0 I upon 4 pi r cube times where we consider an elementary loop delta C prime, and which bounds an area delta S prime. So the result is mu 0 I upon 4 pi we rewrite it as mu 0 upon 4 pi delta m cross r by r cube, where delta m is I times delta s vector. So note that for an extended area, a curved area, we cannot specify such vector, no sense. Then we have to divide the entire curve into elementary entire area into elementary areas, and due to the circulation all the intermediate branches, the current will be cancelled, only the current persists at the periphery. and so that the entire area can be looked upon as the sum of individual areas, individual elementary areas, and we are applying the theory to one such elementary area. Before going to put a name for delta M, let us calculate the corresponding magnetic field. Again, this is delta means the magnetic field at point P due to an elementary area bounded by a contour delta C, bounding area delta S prime, and this is the corresponding contribution to the field. So this is mu 0 upon 4 pi is constant, then curl of this part. We consider the quantity in the numerator as the vector function and that in the denominator is the scalar function. So we write it mu 0 upon 4 pi curl of delta M cross R by R cube plus gradient of 1 by R cube cross delta M cross R. Here we have used the identity that curl of phi cross A is equal to phi times curl A plus grad phi cross A. Let me first evaluate term one by one. Consider this term. For an elementary ring, this area is fixed, so delta M is not changing. So you consider delta M to be a constant vector. It is a constant vector. So it will operate on this. So first term is delta M will come out and there will be dot between this. So the dot is in the second term. There will be a dot between these two and R will come out, but note that delta will operate on R, so we write it as delta M grad nabla operating on R. This is simply 3, and for this part if we write it, this is delta mx del del x plus delta my del del y plus delta mz del del z. This operates on R, means I cap x plus j cap y plus k cap z. So when this operates on this, it is simply I cap delta mx, and this when operates on this and these are 0. So the result is I cap delta mx plus j cap delta my plus k cap delta mz. This is delta m. So this is minus the first term is worked out. Now come to the second term. Second term, this is For this we write minus 3 by r cube r cross delta m cross r. So apart from minus 3, this is r squared delta m. Sorry, this is to the power 5. R squared delta m minus delta m dot r times r. So this is equal to this is minus r cube upon r to the power 5. No, note a correction there. This is plus 3. So if we use this, mu 0 upon 4 pi is there. For the entire term we write 2 delta m upon r cube, and for this we write minus 3 delta m upon r cube plus 3 delta m dot r by r to the power 5. So on simplification, this becomes mu 0 upon 4 pi. Note that this term is negative. Compare this with the electric field produced by a dipole of moment p at a distance epsilon. So this is, let me first write. This is, if we have a dipole of moment p, if we want to find out the field at a distance r from the center, it is the field, and this is the corresponding field due to the dipole contribution. So in electrostatics, the dipole moment p and delta m has the same role. That's why it is called dipole moment. It is a very interesting or important quantity in physics. If we want to study spectroscopy, in spectroscopy, that is the transition of atomic electron from one state to another state, it is found that the electron revolves around the nucleus in an elliptic orbit at a very high speed. The frequency is of the order of 10 to the power 15 hertz. So the electron appears to form a continuous current distribution. So In that case, we can assign a dipole moment to the orbiting electron. The dipole moment is the circulating current times the area of the elliptic path, because the dipole moment is defined as the current time, circulating current times the area traced out by the closed loop. And it is found that when this dipole is placed, a dipole of dipole moment delta m is placed in a magnetic field, then it will have a potential energy exactly similar to the electrostatic case. The potential energy will be, and it also experiences a torque which is delta m cross b, which we shall show you later. And this potential energy causes a shift of the energy levels and leading to the what is known as Zeeman effect. The higher order terms of the multipole expansion can be calculated, but the mathematics involved is very tough, and that's why people do not in general go for the quadrupole calculation of dipole moment vector potential. One thing may be of interest, that what happens to the multipole expansion of A when we use a volume distribution of current instead of current loop. For a volume distribution, so let me write the multipole expansion due to a volume distribution of current. In that case, the dipole moment vector dipole potential is given by mu 0 upon 4 pi integration j of r prime dv prime. When we consider this is the volume over volume v prime over which a current is distributed, we consider an elementary volume around r prime d. Then by r is the distribution. We first one thing, we make a shorthand of the notation, that is, this is equivalently written as prime, just to make reduce the labor of writing. We just introduce a shorthand notation. So in that notation, this is mu 0 upon 4 pi and as usual we expand 1 by r. You note that for a closed current loop, the quantity was I dr prime. This I dr prime has now been replaced by j dv prime. For surface distribution, it would be js prime ds prime. So this is the vector multipole expansion. We write it as The calculation is very tough. We shall just show that the monopole contribution vanishes even in this case. A monopole term. Let me consider monopole term. This is A at L is equal to 0. Because this is 1, this is 1. So the thing remains to show that this is equal to 0. To show that this is equal to 0, we start with writing J. J is written as summation over EI cap JI. I is equal to 1 to 3. It means this is I cap JX prime plus J cap JY prime K cap JZ prime. This is written in a compact notation. Now JX is as Jx prime is equal to I cap J prime. This is we have written, and I cap is can be written as this. Nabla prime x prime is equal to I cap. So we can write it as this is for the I cap. This is the concept that has been used. Let me explain it. This is I cap del x prime. I cap del x prime plus j cap del y prime plus k cap del z prime operating on x prime. So this is simply I cap. Similarly, when nabla prime operates on y prime, it gives you j cap. That is, we have used here. Now, EI cap is there. This part we write it as it will have two terms. One is, this is the divergence. It will have one term, that is this, and the extra term that has been added has to be subtracted. That added term is if the current is solenoidal, this is equal to 0 for J prime solenoidal. In the magnetostatics, development of magnetostatics, we develop in such a way that that J prime is solenoidal, J is solenoidal in the static situation, so it is the term. So this simply is now if we like to now carry out the integration. So first let me summarize what we have done. J prime has been written in component form. Then we have used the definition of finding out the components of the vector. The trick, then we have used a trick to replace the unit vector in terms of the gradient of the coordinates, and then after manipulation we have assumed that the vector potential, the current density is solenoidal, so we land up with this result. Now they come to the integration part. Remember this definition, we will come to this definition afterwards. So the def A0 L is equal to 0 at R is equal to mu 0 upon 4 pi R, mu 0 upon 4 pi R. Then we have J prime dV prime integrated over V prime. Now we have, let me do a trick. We have current distributed over this region. We use a larger volume, tau prime, and the surface is sigma prime. In this region, the extra added part, the current density is 0, and current density is in general non-zero within the volume. So we have added an extra part without any loss of generality. So we write it as mu 0 4 pi R integration over tau prime. Now for this we write, for this part we write and this is written as mu 0 upon 4 pi R summation over I EI cap, then this integration divergence prime. This we convert this integral into a surface integral. So we write mu 0 upon 4 pi R summation over I EI cap, and the rest of the quantity is since the surface is far away where the current density is 0, so the result is 0. So we see that the monopole contribution to the magnetic vector potential is 0 even for volume distribution of current. Only thing is that for filamentary wire or one-dimensional conductor or for a closed conductor, the calculation is very simple, and for volume distribution the expression or the mathematics involved is very tough. So we do not go to the detail of the calculation for the vector potential, dipole contribution to the vector potential, but rather we make an analogical treatment. So with the analogy of one-dimensional case, we shall derive from the dipole contribution to the vector potential for volume distribution of current. The dipole term for 1D conductor, the dipole term was mu 0 I upon 4 pi r cube where ds is the area formed by the loop. So if we consider this is the part of the loop, this is r prime and this is dr prime. So ds prime is this area, so ds prime is equal to half r prime cross dr prime. So in that sense we write it as an extra half will be there, and this is cross R. So we write the dipole moment contribution to be like this: mu 0 upon 4 pi m cross r upon r cube, where m dipole moment for 1d we write it as I by 2 dr prime. The form of the vector dipole contribution remains the same for 2D and 3D conductor. Only thing is that this part changes. So dipole moment for 2D conductor is half, this is integration over s prime and for this is the class. So we use the same definition, and the fact that I dr prime is replaced by js prime ds prime or j prime dv prime, whatever the case. Either we use this and the same definition, and dipole moment is this. But for an elementary loop, current loop, the dipole moment has a very simple physical significance. In that case, if we have a elementary closed current loop, then the dipole moment is simply the A vector area times the circulating current. That's all about the theory on magnetic vector potential. In the next lecture, we shall take up the application of vector potential in few simple cases.